Hello everybody, my name is Daniel Legge. I am working for IBM Quantum based in the Zurich Research Laboratory. And today I will be talking about multi-objective optimization. More specifically, we'll be looking at how we can leverage the quantum approximate optimization algorithm for multi-objective optimization. And the work that I will be presenting today is based on this paper recently published in Nature Computational Science. It is the result of a collaboration from the optimization working group with people from the Los Alamos National Laboratory. In fact, I'm filling in today for Elijah Pilowski. But we also have people from the Zuse Institute in Berlin, for instance, Thorsten Koch, Stefanie Riedmüller, and Aisha. So the guiding questions to the research that I will be presenting here are the following. Can we find optimization problems that are harder for classical solvers than the currently studied ones in the field? The second guiding question, what can quantum computers do particularly well, and where can we leverage that in optimization? And then, of course, we want to find an overlap between these two guiding questions. So in particular, the problem that I want to look into today is multi-objective optimization. This is something that is prevalent across industry, and in fact, a lot of interesting problems are in fact multi-objective optimization problems. For instance, you can think of portfolio optimization. This is inherently a multi-objective optimization problem. On the one hand, you would like to optimize your return from your assets while minimizing the risk that you have here. So in multi-objective optimization, what we have is several objectives that we need to simultaneously maximize. And importantly, these objectives may be conflicting in nature, meaning that the solutions that we are looking for form what we call a Pareto front, shown here as the green curve. So when a point is on the Pareto front, it means that if I want to increase the value of an objective, say for instance, if I want to increase the value of F1 here, I can only do so by paying a price in the other objective, right? So this is actually the definition of the Pareto front. Now, we measure how well we are doing by calculating what is called the hypervolume, shown here in green. And this is actually classically hard for relatively small problems and for a moderate number of objective functions. And this is what makes this class of problems interesting to take a look at. What's more is that there are solutions here on the Pareto front, which we call non-supported Pareto optimal points, which are very difficult to find classically. And the definition of these points, like the one shown here in green, is that it is not on the convex hull of the Pareto front, as shown by the dashed blue line here. So in the rest of this work, we will be assuming that the objective functions are quadratic in nature, and the decision variables are binary, meaning that they take on the value of 0 or 1. So to address these problems, what I want to do first is to look and review the classical algorithms that work well. The first one is the weighted sum method. This classical algorithm functions in the following way. I will first draw vectors from the unit sphere here, these C vectors, and then for each C vector that I have drawn, I will aggregate my objective functions into a single objective function. And then we try and solve, for instance, with Cplex or some other classical solver, this single objective function. And then the resulting solutions here will form an approximation to the Pareto front. So looking at this visually, we have two objective functions here, f1 and f2. And if I choose a linear combination of both of these, c1 times f1 plus c2 times f2, I get a vector here. And then I try and maximize along this direction. And the point, which is the closest to satisfying this problem, is the one shown here in black. So what is nice with this procedure is that it returns only Pareto optimal solutions. However, it can only find supported solutions on the convex hull, meaning that we'll have a hard time finding these type of points. Now, a second classical method is the epsilon constraint method. The idea here is we first maximize each objective function to get lower and upper bounds for these functions. This is the first step. Then we need to draw k random samples from an interval on these lower and upper bounds. A second step is we need to draw k random vectors, as before. And then we will now, for each pair of c and epsilon sampled in the previous two steps, we will solve the following optimization problem. We will maximize the linear combination of objective functions weighted by the c vector, and in addition to this, we require that every objective function here is larger than the given epsilon, right? Visually speaking, what this does is the following. You can see here that I have this c vector, as in the weighted sum method, but now we have these constraints epsilon 1 and epsilon 2. And in the case that I have drawn here, this will in fact allow us to find this non-supported point here shown in green, right? So this is once again a method to provide us with Pareto optimal solutions. It can find non-supported solutions, which is very nice, and it converges to the optimal Pareto front, right? However, one of the prices that we pay is that the problem is more complicated. You can see now that I have a maximization problem with constraints, and this can make things a bit harder. And finally, the other method that I would like to present is the defining point algorithm. This is one of the state-of-the-art methods to address multi-objective optimization. You can see here that the paper was published very recently. And the way that this proceeds is that it's a variant of the epsilon constrained method. And the way that it works is that it builds boxes around regions in the landscape that we do not need to explore anymore. So basically, this means that in these white regions, we will actually start to sample more. And this then allows us to return only Pareto optimal solutions. It can also find non-supported solutions, as before, and it converges to the Pareto optimal front, right? So this is one of the state-of-the-art algorithms that we will be comparing to. So, a quick summary of the classical approaches. Every point on the Pareto front corresponds to solving at least one optimization problem. Oftentimes, it requires more. The number of points on the Pareto front can grow very quickly. I'll show a few examples of this later on in the presentation. Now, randomized variants of algorithms converge only very slowly to the optimal Pareto front, even though each individual objective function might be efficiently solved classically. Non-randomized variants of these algorithms are difficult to parallelize, since you might be recomputing the same point multiple times. And then finally, there are a few heuristics that I haven't presented here, like for instance, based on genetic algorithms that require often a lot of manual tuning. So, turning over to Quantum. How does Quantum deal with optimization problems? The algorithm that we often use is the Quantum Approximate optimization algorithm. This was published by Ed Farry in 2014. So let me quickly recap how this algorithm works. Basically, the steps are the following. We take our optimization problem and convert it into an Ising Hamiltonian such that the ground state of this Ising Hamiltonian is in fact the solution to the problem that we want to solve, right? So if, for instance, this graph here corresponds to the topology of my problem, then this is the Ising Hamiltonian that might come out of it, right? It is made of 2-qubit terms and single-qubit terms. Now, the QAOA algorithm is in fact a trotterized version of adiabatic annealing. So we will be alternating between p layers of a cost operator, which is the exponential of this Hamiltonian, and a mixer operator, shown here. And then the time steps here in this trotterization, they are left as 3 parameters that we can optimize in order to try and draw good samples from the quantum circuit, right? So the rationale as to why this algorithm works is simply based on adiabatic quantum computing. If I start off in the ground state of my mixer operator and I apply an adiabatic time evolution, I will then end up in the ground state of the cost operator HC. So what is nice with this is that we can already execute it on existing hardware. We don't need to wait for fault tolerance to start to explore how this algorithm works on the hardware. And in some cases, this heuristic method also comes with provable performance bounds. This is the case in, for instance, MaxCut with 3 regular graphs, where people have actually computed approximation ratios for this algorithm. So how do we get good quantum states, right? We need to have strategies to determine good QAOA parameters. And by good QAOA parameters, I mean these gamma k's and beta k's here in the circuit, right? So variational training on the quantum hardware is possible, but it does take a lot of time, and we need to navigate a complicated landscape here. But fortunately, we don't necessarily need to do that. There are ways, in fact, to get good parameters inspired from annealing, or we can leverage the concentration or transfer of parameters from small instances to larger ones. And this is, in fact, something that we will be leveraging in this work. There's a few other methods that one can also take a look at. Machine learning is also something that has gathered a lot of attention recently. And some of the methods that I'm listing here are also implemented in this open source package called the QAOA training pipeline. Now, let's take a look at the quantum algorithms for multi-objective optimization. What I showed to you in the previous slides was QAOA for single objective, the standard variant. So how do we change this? So in multi-objective optimization, we are interested in quickly generating a diverse set of good samples in order to explore the Pareto front, right? And this also means that good suboptimal solutions can also be important and interesting, because maybe with a little bit of classical post-processing, we can actually convert them to solutions that lie on the Pareto front. So the approach that we have in this work is based on QAOA. We'll be supposing a kubo. And what we do is we first optimize the QAOA parameters for a representative single objective. And the way that we create this single objective is we simply average equally all of the Ising Hamiltonians, right? So in effect, this basically means that we have a C vector that corresponds to 1 divided by the number of objectives, more or less. So let's say that we have trained good QAOA parameters. Then what we do is we draw C vectors here at random. We draw K of them. And then we will try and run the QAOA for a cost function that is the linear superposition of all of our objectives, as shown here, using the QAOA parameters that we found under step 1, right? So this is where concepts from the transfer of parameters start playing a role. And then the samples that we obtain from the QAOA will actually be the samples that we use to try and reconstruct the Pareto optimal front. So if you think of it, what is happening is the following. We're creating a linear combination of our functions, as shown here. And then with the QAOA, we will try and sample good states here around this area. So a few things to remark. There is no guarantee to find Pareto optimal solutions by doing this. It's once again a heuristic method. But through, let's say, some of the intuition that we have from QAOA, we believe that we should be finding solutions that lie fairly close to the Pareto front. Now, importantly, we might also find non-supported solutions, as indicated by this purple dot here. And importantly, there is no need to retrain QAOA, right? We simply replace the Hamiltonian parameters. So leveraging, once again, the concepts of parameter transfer. And hopefully, what we can do is we can very quickly sample a diverse set of good solutions to build up our Pareto front. So the way that this looks in terms of a quantum circuit is the following. This is the standard QAOA circuit, but you can see now that the cost function Hamiltonian is in fact a superposition of multiple objective problems, as shown here, right? But otherwise, the circuit looks a lot like standard QAOA. So in the next few slides, I want to go over the results that we have obtained for this work. So we looked at 2 different types of problems, 2 different sizes. We'll be looking at the multi-objective maximum cut. We define these on graphs that are native to the heavy hex of our hardware. And a lot of the results that I will be showing are for these 42 variable instances shown here. But we also considered smaller instances with 27 variables. Now, the graphs that we have, while being heavy hex, they have edge weights that are drawn from a random distribution here, drawn from a uniform distribution with mean 0 and standard deviation 1, right? So we are in fact solving multi-objective weighted maximum cut problem. Now, I want to give a little bit of intuition here as to why these things are hard classically, right? So let's say I take a single maximum cut objective function and I ask gurobi to find the solution of this. Well, gurobi runs extremely quickly, right? With this classical method, or this classical solver, I can solve one maximum cut objective in less than a second, in a fraction of a second. The number of points here is of the order of maybe one or two optimal solutions if you take into account the symmetry of the problem. Now let's say that I add two additional objectives, right? So I have a total of 3 objective functions, and I try and find the Pareto front for this. It takes gurobi about 4 minutes to solve these 3 objectives. And now we have a total of around 2,500 points on the Pareto front that we need to deal with. And let's just say that I add one additional objective going from 3 to 4. What you'll see now is a drastic increase in the time it takes gurobi to find this Pareto front. We go from 4 minutes to 3 hours simply by adding one objective function, right? And the number of points on the Pareto front is now on the order of 50,000, right? So we have problems, objectives that by themselves are very simple, but when you start adding a lot of them together, then the problem becomes computationally, classically very challenging to do, right? So this is kind of answering one of the guiding questions that I set out in the beginning of this presentation. So the way that we did this with quantum is with the algorithm that I presented in the previous slides. And to find the parameters for the larger 42-qubit instances, we trained good QAOA parameters on the 27-qubit problem here using the package Julie QAOA. And then we transferred these parameters from the small instance to the larger one, right? Now, the qubits that we select on the hardware are simply chosen in such a way that we maximize the fidelity based on the calibration data provided by the backend. And finally, one point to mention also is that we do not do any error mitigation or suppression. We just run the raw circuits and take the samples out of these circuits to build up the Pareto front. Now, on the hardware, we executed 5,000 random objective weights, C. So these are the C vectors that we sample. And then for each C vector, we take 5,000 shots per circuit, right? And so this means that in total, we will be gathering 25 million shots from the QPU. And at the time when we executed this, it took about 45 minutes of runtime to gather the data, right? So put this a little bit in perspective with the runtimes that we gave on the previous slides. Now, to validate and first check to see if actually a QAOA approach makes sense, we did first some classical simulations of the circuits using matrix product states. So we are approximating what the circuits are doing, and we have here 6 different results. In each panel, you will see QAOAs of different depths, ranging from depth 1 all the way to 6. And what is changing from one panel to the next is the bond dimension. So the larger the bond dimension, the more faithful the MPS approximation of the quantum circuit will be, meaning that we're capturing more and more of the entanglement effects that take place in the circuit. So at a bond dimension of 1, we're not really capturing many entanglement effects. Now, I want to also explain a little bit to you what are the different axes on the plots here. So these plots, we'll be seeing them again and again throughout the remaining slides. On the x-axis, I have the time it takes to generate the samples. Now, in these particular simulations, this is a fictive time. In the sense, what we're doing is we are saying that each sample can be generated at a rate of 10 kilohertz. And this is the rate at which you get from a quantum computer, right? So we're kind of pretending that the MPS is a real quantum computer by saying this. So it gives us an indication of how fast things should be running on the quantum. It's also an idealistic setting because it only considers the QPU time. So this explains the x-axis. Now, on the y-axis, we have a measure of quality. And in fact, the closer we are to this red dashed line, the better. And this red dashed line corresponds to the largest hypervolume that we were able to find with all of our methods. So let's go back to the content of these charts and take a look, right? If we have a MPS simulation with a very low bond dimension, we will see that as time passes, we don't really increase quality all that much. And all the different depth QAOAs give the same results. And this is kind of to be expected because at a bond dimension of 1, we're not capturing any entanglement effects. Now, what is interesting to see is that as you start increasing the bond dimension, you can see better and better performance from the QAOA, right? And also, as I increase the QAOA depth, we start to see better performance as well. So the more one of these curves is towards the left, the better it actually is, because it means that I can generate a higher hypervolume in a shorter amount of time, right? And you can see here that as you increase the bond dimension, the depth 6 QAOA is doing sort of the best over here, right? So this is a very nice indication that the QAOA is able to give to us solutions that lie on the Pareto front, which is what we are looking for. So let's turn now to the experiments that were executed on the quantum hardware. You can see here in the first column the depth of the QAOA that we ran, and then correspondingly in the second column here the number of 2-qubit gates in the circuit, right? So a problem instance with 42 qubits on heavy hex and depth 6 QAOA requires about 552 controlled Z gates. The duration of these circuits is still very short compared to the T1 times of the qubits. We're talking of a duration on the order of about 6 microseconds. And finally, you can see here that as you increase the depth of the QAOA, the fidelity starts to drop. Now, this fidelity metric here is computed simply by taking the fidelity of the individual CZ gates and multiplying them together, right? So in the end, we have a fidelity that is a little bit over a few percent here. So let's take a look at the results. You have here 4 different plots. They correspond to depth 3 QAOA, depth 4, 5, and 6. Now we have results from the real hardware, from the MPS, and from the classical methods. So first off, these solid lines here, they correspond to the MPS results that I've shown to you on the previous slide. Now, the dashed lines here, 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 and here correspond to the results from the quantum hardware. The device that we ran this on was IBM FES. And then we add onto these charts the runtime from the classical methods that I showed to you. So you can see here that the method that reaches the largest hypervolume the fastest is this defining point algorithm shown here. Now, what is very interesting to see here is that the execution time, or this fictive execution time of the MPS, is actually beating this defining point algorithm here. And so what this is telling us is that if the quantum computer didn't have any noise, we would expect to see a convergence here that is faster towards the hypervolume than the DPA algorithm found. So this is already very, very exciting point and shows that actually multi-objective optimization is a very interesting direction to pursue to find a quantum advantage. I want to show here the optimal Pareto front that we found from the hardware. You can see the 3 different objectives for the max cut, and then all of the points here are in fact samples returned from IBM FES. Right, so this kind of corresponds to the solution of the multi-objective optimization problem that we were setting out to tackle. Now, I want to present a little bit of insight here into and connecting to some work that we did in provable bounds for noise-free expectation values. So in this paper, published a couple of years back, we showed that simply by taking more samples, you can compensate for the noise that there is on the device. So we apply a very simple rescaling. If you remember the fidelities that I showed to you a few slides back, what we do is we do the following. We take these fidelities and we simply divide the curves from the hardware here by these fidelities, right? So we're essentially saying that if I wanted to arrive at a noiseless result here for depth 3 QAOA, I would take the hardware result and divide the time by this value here or actually multiply the time by this value. And what happens is the hardware result that used to lie around here is now moved forward in time. And what this shows is that there is a very nice agreement between what the MPS predicted in terms of convergence here and this rescaled hardware result. So once again, these provable bounds for noise-free expectation values gives us some insight, or gives us the tools to gain insight as to how the algorithm would actually end up running on noiseless hardware. So what this means is that I can take the results from the noisy hardware, I can rescale them to account for the sampling, and then I can get insight as to how this would perform in a noiseless setting. And we see indeed excellent agreement between these rescaled hardware results and the MPS results, which I think is a very nice insight and allows us to predict the performance of heuristics that will be run on noise-free quantum hardware. So with it, I would like to conclude this presentation. Basically, what we did is we looked at multi-objective optimization on 42 qubits. Each individual problem could be solved very easily and efficiently with classical methods, but when you are dealing with multiple objectives simultaneously, it becomes very difficult. And this is what makes it a promising candidate problem to do, or to look at, to find an advantage in quantum optimization. So some of the next steps that we have actually planned for our own research is to scale the problem size, density, and the number of objectives, right? So making it even more challenging. We want to extend beyond the simple max cut problem. And then we further want to improve the quantum algorithm, maybe by post-processing the samples classically, or doing some adaptive quantum classical algorithms. And so with that, I would like to thank you a lot for your attention, and I will end here. Thank you very much.